first to our audience. So Carlos is a PhD in photonics, SECPHO, and I'm very glad that he's here because I've been able to follow more or less his career since he more or less started. And he did very, very great results in the research and the applications of quantum technologies, cybersecurity, quantum random generation. And from all these ideas, he was able to start and to co-found a new company, a new venture called QSight Technologies. That is a spin-out from MICFO, founded in September 2017. And he's very well known in the world and in Europe. As you can see here, he is one of the under MIT Innovators 35 under 35. So it's a great pleasure having you with us. So now let me give you the role of presenter, and you can show us your talk. Thank you very much, Carlos.
Okay. Can you help me? I do not see how to select the presentation.
So can you go to share application?
Yeah.
And then you can share PowerPoint and your exactly. And here we see quantum technologies for data security.
Perfect. Okay.
All yours.
Thanks a lot for this super warm introduction, and I'm very happy to be here speaking to all of you. I'm going to be focusing on a radically different scale. Let's say it's a very applied talk now. So I'm going to be talking on how quantum technologies are already helping in improving data security. And I'll start in a very let's say basic stage, just to set the grounds on what I refer with data security and how quantum technologies can help. So basically, you know that communications have changed our society, but it's not just communications that have changed society. It's actually the fact that we can communicate in a secure way, right? If we would not be able to communicate in a secure way, most of the things that we do online would not be possible, like sending an email. We would not be sending most of the emails if anyone could read those emails, or logging into our bank account. So really, security has been as important as communications in many aspects of the transformation. And it's also playing a very important role in new emerging markets, like, for instance, examples like self-driving cars, right? So even today, cars can slow down if you get very close to the car in front in the highway, and they slow down on your behalf. That means that all of this control is digital, and that means now that if a hacker can hack into your car, this hacker can now activate your brakes and cause you to crash, right? So security is playing an increasingly important role in society. The slight problem that we have is that the encryption technologies that we use today have limitations, right? Tony already I've talked a little bit about this, and also Enrique, and this is what I would like to dive a little bit deeper now. So, and the first thing is clarifying some of the maybe diverse concepts that you can find online when you look about these things, and I'm going to be framing it a lot of people call the quantum threat. And what does this mean? So basically, we have today data security or encryption, cybersecurity, that's based on problems that are very hard to solve. And Tony already explained a lot about this, so I will move quicker here. It means that we based the protection of our data on problems that we believe are hard. Problem is that a quantum computer is, especially a Shor algorithm, as Tony explained, can turn these hard problems into easy problems, and therefore it means that the security is no longer holding. So all of our infrastructure will be vulnerable. And Tony mentioned something that's very important. It's not only a quantum computer that can cause this threat. It's also a breakthrough in mathematics or cryptography, because actually there is no proof that this problem is hard. It's just that we believe it is hard. And this brings me to the second or the next step, which is upgrading this really unsafe system that we are handling today. And this is basically based on using problems that are harder to solve. And this is typically known post-quantum cryptography. And this is a name that is very poorly designed, because it's not after quantum. It does not mean that this comes after quantum. It really means that you should be safe with these problems against a quantum computer that, as we know it today. And basically here, the point is that we are semi-safe against quantum computers or against threats, because in the same way as today, it's going to be based on problems, and it's going to be based on assumptions about the hardness of these problems. And this is quantum cryptography. What else can we do, or what would be ideal, is to have security that is based on proven security methods or technologies. And this is what I call future-proven encryption. And here we have quantum technologies, as I will be talking later, that can turn all of these threats about quantum computers or even mathematics into, in a totally safe way. Let's say if we move into these future-proven encryption technologies, there is no danger that a quantum computer will be able to break it, because it's going to be based on fundamentally unbreakable technologies. And I'm going to go deeper on that. As a final comment and as a final jargon for you to look at is that some people call this combination of post-quantum and future-proven quantum-safe cryptography. So now the question is, when should we become safe against this quantum threat? And actually, if you ask a lot of people, the answer is now, for a very simple reason. The first one is that, as I said, we just believe that we are safe, but we do not have proof, right? It might be that someone can decrypt our messages today in our communications. And the second one is this concept of store today and decrypt tomorrow. So basically, if we assume that we are safe today, I can store communications with the promise that when I have access to a quantum computer, I will be able to decrypt those things. You might think that that's not relevant, but think about medical records for you that should remain safe for many, many years and decades. So basically, it's information that we need to protect today if we want to be safe tomorrow. So how can quantum technologies help us move from today's vulnerable systems or limited systems, if you want, to stronger cryptography? I will make a detour a little bit and talk about encryption. So in encryption, there are three main things that we need to do right. The first one is, here in a very, let's say, general terms, hiding mechanism or an algorithm. And to understand this, think about having a message, running it through this algorithm, and what's at the output? It's a complete gibberish of letters, right? It doesn't seem to make any sense. Problem is that we all use the same algorithms, of course, because otherwise we would not be able to communicate. So this does not provide security, because anyone can apply the algorithm in one way, apply it in the other way, and reverse the process and get the message. So what we do is we need this second block, which is we need to add to this recipe an unpredictable secret. So basically, we now combine the message that we want to send with this secret that we are the only one to know, and then we run the algorithm, and we upload this to the cloud, let's say, or we send it through email via servers, whatever. So now, if someone gets access to this encrypted message, they cannot reverse the algorithm because they're missing the secret. They do not know the secret. And that is essential for security. Basically, there is the Kirchhoff principle that says that the unpredictability of the key, of the secret, is actually the only element of the security chain that provides security. So, okay, now we can encrypt messages in a secure way if we do these two things right, but we have a problem, and is if I want you to read the messages that I encrypted, I need to share the secret with you. So we need technologies to do secret distribution. It's also called key exchange. So we need to do these things right. When we're talking that current systems have limitations, it's because we are not doing them in a provably secure way. Let's say both the hiding mechanism and the secret distribution and the key generation are run typically with algorithms based on hard problems. So this is where quantum technologies come in, and we have two types of technologies that can help. One is quantum random number generators. Basically, it allows us to generate really unpredictable secrets, things that no one else can guess because it's based on sampling a physical process, a quantum physical process. And as Tony and Enrique mentioned, measuring quantum systems have unpredictability inherent because of all of these superposition states and really the core foundations of quantum physics. And the second thing that can help us on the secret distribution part is quantum key distribution. And I think in the next talk you might hear a little bit more. but I will just, so I will focus my talk on the random number generation part, but I'll just give you one example that actually I've mentioned before, and it's the fact that quantum key distribution is already a technology that you can buy, and it's a technology that a lot of, let's say, people are investing money on. And this is an example on a satellite that China launched and allowed them to do key distribution, so exchanging a key between two locations, one in China and the other in Austria, so basically more than 6,000 kilometers. So it's an embryonic technology, let's say, that was a proof of concept launch, but it's really happening, and it will be here before we realize. So just to wrap up until now, so basically there are three things I think that are important to remember in this topic. The first one is that data security has limitations today, and we have to be aware of that thing because that brings risk in our products and infrastructures. There are next generation encryption technologies that are being developed, both in post-quantum cryptography and in future-proven encryption technologies. And quantum components can offer us access to long-term safe solutions. And I will elaborate a little bit more now on one specific component, that is the random number generation. So this is a little bit second part of my presentation. And I will start with a brief introduction to the field before diving into how we are building these components today. And this is what I was mentioning, that unpredictability is a source for the information era. But it is actually hard to get, because strictly speaking, in classical physics, there is no unpredictability. It's just lack of knowledge. And in quantum physics, we can get it. But that means that we need to sample a quantum process. The good news is that actually the first random number generators or the ideas were proposed in the 50s. And already in the 90s, they were coming close to the practical domain. And this is one of the first papers that transformed the field. And it describes a random number generation mechanism that I will describe to you now. So imagine that you have a device, and this is a box that can generate photons, which are particles of light. Right? So now these photons are quantum particles, and what we do is we send these photons into a device that's called a beam splitter. And basically this device, what does is with 50% probability, it lets light go through, and with 50% probability, it reflects light. I don't know if you can see my mouse, but somehow this is one.
Yeah, Carlos, we can see the mouse.
Perfect, thanks. And this is the other possibility. Because this is a quantum particle, it cannot split. And here it comes one of the funny things of quantum physics, which is a superposition state. So basically the particle is in a superposition of being reflected and transmitted. So now what we do is we place two single photon detectors, so devices that can see just one particle of light. And whenever we see a click in this detector, we will say that we have generated a 1. And whenever we've seen a click in this detector, so that this detector has measured something, we will say we've generated a 0. So this is an iconic implementation of a quantum random number generator. It's very simple. Problem at the practical level, it has some inconveniences because we need these single photon generators that are not available on the marketplace, and single photon detectors also tend to be a little bit cumbersome. So there's been a lot of research on how to use different quantum processes that are much simpler to use in practice. And this is what a series of proposals that are based on using macroscopic states of light. And a little bit, the three of the most famous is this first publication that is based on measuring phase noise in continuous wave operated lasers. There is another one that's based on measuring homodiene or vacuum fluctuations in a homodiene detection scheme. And this one that is again based on measuring a phase noise or phase diffusion in a laser, but instead of in a continuous wave laser, in a gain switch laser. And this is the technology that we're developing at QSide, and that I will elaborate a little bit more. Before diving into it, just some of the key features that we want in practice for these technologies to be relevant for applications. So we need random numbers that are unpredictable, and that's why we use quantum technologies, because quantum physics is the only way that we know we can go and find unpredictability. We also want them to be small, because we want to protect all of the devices that connect online, and that means we need to protect a wide variety of components, from servers in data centers to small sensors in IoT networks. because we want them to deploy at this scale. And for this type of very inexpensive devices, we need this component to be inexpensive too. Otherwise, at the practical level, it's going to be very hard to deploy them. And because the volumes are very high, we need these technologies to be very scalable in terms of volume. So we need to have a process that can be industrialized. And finally, we also want them to be fast, because the requirements for encryption and the amount of data that we protect is increasing continuously. So basically, these are 5 of the features that we demand for a random number generator to be used in cryptography. And let me tell you, just to go to the end of this introduction to using quantum technologies for security, about the entropy sources of the random number generators that we are developing at QSight. We use a process called accelerated phase diffusion technology, and I'm going to be describing it briefly because it's actually not complicated to understand. So we take a laser diode and a laser source, and because it's a diode, it has mainly two states, when it is off and when it is on. And what we do is we switch between these two states continuously and very fast. So we generate this type of optical pulses, and if you do this properly, the phase of this pulse is going to be random from time to time. And the reason it is random from time to time is because when the laser is off and it's properly switched off, you have a process that's called a spontaneous emission, that is a purely quantum mechanical process. So basically, we amplify this spontaneous emission, which is a microscopic quantity hard to measure, into macroscopic variable, which is an optical pulse with millions of copies of that phase. So what we do is we now put an interferometer, that what it allows us to do is convert these random phases into random amplitudes, and then we photodetect that with a normal photodetector. And I wanted to describe this because actually all of these technologies, all the technologies required to build this scheme, are commercially available. And that means that we can use processes that are already mass-scale manufacturable to build our technology. So we've been working on this for a number of years at SECPHO. So QSight is a spin-off company from the Institute of Photonic Sciences, and basically we managed to not only demonstrate the principle behind all of it, but also build prototypes that were used in fundamental physics experiments to prove the foundations of quantum mechanics. And also, we managed to demonstrate the integration of this technology into a single photonic chip. And as I mentioned, this is technology that can be mass-scale produced. This chip was done in collaboration with a number of partners, including VLC Photonics, which we'll be talking in the next talk. So basically, this is one of the products that our company is working on. It's the first fully integrated quantum random number generator. It can generate multiple gigabits per second in an area below 3 by 3 millimeters, and because of all of these features, it's actually a unique device. Before I leave, just mention that we are part of with QSight, the spin-off company of 2 of the quantum flagship initiatives. One is the CIVIC project that is building key distribution technology for data centers, and QRange, which is aiming at developing cheaper, faster, and more secure random number generators from the industry. So this concludes my presentation, and I'd be very happy to answer any question that you might have.
Thank you very much, Carlos, for this very interesting presentation. I repeat that if someone has a question, they can write it on the public chat. In the meanwhile, I would like to ask you, we've been talking about quantum random number generator. But I've heard in the past, since, I don't know, not that long ago, let's say a decade ago, some people are already selling quantum random number generators. In what context does companies use it? Could you tell us a few words?
Okay, can you repeat the last part, because there was noise and I missed it.
Okay, sorry. So I've read sometimes that there are some companies developing already quantum random number generators, and that they sell them. So I'm just curious to know what type of companies buy these sources and these devices, and what's the market behind it right now?
So in terms of the existing companies, so actually you're completely right. And as I was mentioning, already in the 90s, there was this first publication that brought light into how to build real devices, and from 2004, there was a company commercializing these solutions. So most of so as far as I know, applications in encryption have been a very relevant use case, especially in data center environments, so really at the infrastructure level, but also in gaming, in applications of online casinos, for instance, and also in supercomputation, right, in problems like Monte Carlo analysis that you need to run randomized algorithms. So these are three examples of applications that these companies have been developing over the years. Problem has been that the size of these devices or the price has not been able to break market barriers to bring into, let's say, IoT arena, and that's most of the effort that these companies, including ours, is undergoing. Really scaling the technology and making it sufficiently small and inexpensive for entering these new markets.
Because now you brought a very good point. So what do you have a rough number? What is the price of one of these devices if I want to buy it right now?
The $1,000,000 question.
Yeah.
So I cannot answer this question, but just to this is a very simple argument, right? If you're buying, let's say, a phone for €1,000, you cannot be paying 500 euros for a chip, right? So really the cost should be meaningful for the target final cost that the device is spending for that type of devices. And this same argument applies for servers or for IoT devices. So if the selling price has a given number, you know that your component needs to be much lower than that.
Yeah, sure. I understand. And finally, just to let the people know more or less the status of the company. So where are you right now? Because you were born 2 years ago. Your company was born 2 years ago. So what's the current status and how you see it in the future, let's say, 5 years?
So the company is spun out from SECPHO at the end of 2017. So we've been growing from that time. We will be a team of 10 people now. And so we're shipping devices for data center applications, for instance, high-speed and compact components for data centers based on off-the-shelf technology. So everything commercially available components, and that is being shipped today. Our main focus is on industrializing the chip technology. That's where we're putting a lot of effort, and we'll see our company really being able to make a difference, really being able to develop and industrialize these components so they can be made available for a wide range of applications with very high performance on top of the scalability.
I'm sure we'll hear a lot from it in the near future. Thank you very much, Carlos, for your talk. So let's move to